So now I'm started to record the lecture, and Marharyta, the virtual floor is yours. Please go on.
Thank you. So you should be able to see my screen now. Yes, I think you do.
Yes.
So let us continue with the second part. As we discussed, there are three parts. The first was introduction, then the causal inference, and causal learning. And today we'll talk about causal inference. And causal inference, if you remember, it's about how to measure the strength of the causal relationship when the graph is known. That is, we know what are the directions of the causal relationships, which variables are causes, which variables are effects, and now we need to correctly measure the strength of this causal relationship. As we saw during the demonstration last time, it is not as trivial as we might think. We should follow some rules to be able to measure it correctly. First, we will start with some theory of structural graphical models. We'll talk about graphs, connections, and how the information flows from one node to another. This might seem a little bit disconnected from the theory of causal inference and causal learning, but we will see later that this theory has very direct application. So please stay with me for some time while we'll be discussing this theoretical background knowledge, because it will be required for us to do both causal inference and causal learning, that is structure learning at the end. So the theory is based on directed acyclic graphs. We'll be talking about directed acyclic graphs. That is, we'll be having graphs as presented here, and the condition is that there are no cycles. And this is a question that was asked last time. So what if we have sort of a feedback loop, that there is a cycle between two variables A and B? And as I said, this situation can be broken down into two cases. When first we have A being the cause of B, and on the second stage we consider the effect that B has on A. So in the theory, we will concentrate only on acyclic graphs, that are graphs that have no cycles. For us, an edge will mean that there is a connection between two variables, and we assume that this is causal connection. And what is interesting, the absence of the edge, for example, this one, has more meaning to us than the presence. Why? Because if we assume that there is an edge, we assume a causal relationship, but the strength of this causal relationship might be zero. And then in this case, essentially, there is no association, there is no any connection. However, when we assume that there is no edge, as for example, in this case, we precisely assume that these two variables are not directly connected. So this course, as I said, is about assumptions, because we always need assumptions to go from purely statistical quantities to be able to measure some causal relationships. And there are also assumptions concerning the graphs. I will not be going into very deep details, but I will be just mentioning some things that are important for understanding. So now our question will be the following. Given a graph with a known structure, what kind of associations or dependencies can be observed in the data set that is sampled from this structure, as shown here? So the question will be the following. If I have such a structure in the real world, in nature, and I can sample from this data, then will I observe any statistical association between two variables T and A, or between variable T and C2, or between variable T and Y, and so on? So this is the question that we'll be discussing now. And later we'll see how it will be used in our causal questions. And to answer this question, we'll consider first the so-called building blocks of the graphs. There are the graphs that are small, they contain only 2 or 3 nodes, and we will use this reasoning to build after that the general conclusions. So let us start with the 2 nodes graph. We have 2 cases.
No.
Yes? Any questions? Okay. So we can have two possible cases here. The two variables, they can be either connected or disconnected like here. And if they are connected, we assume there is some causal relationship, and naturally these two quantities will have some association in the data set that we sample. This case, as we said, a stronger assumption for us, absence of the edge means that they are independent. There is no any link between them, so we assume that they're independent. And in the data set that will be sampled from this situation, there will be no statistical relationship or statistical correlation between these two variables. Now let us try to add one more node and see what will happen. We'll not be considering this structure because whenever we'll be adding one more node to this structure, let us say for example like this, then we come back to the previous situation. Two nodes are not connected and two others are connected. So we will consider this structure as the baseline and we'll try to add one more node to it and see what will happen. So there are three possible ways how we can add one more node to this structure so that it is connected to the previous nodes. One possible way is like this. And in this case, we will get a structure known as a chain. Now we know that the two nodes that are directly connected will always have statistical association between them. The question is, will the statistical association flow between the two nodes that are not directly connected, that have no direct causal relationship between them? And to illustrate the solution, I will be using like a sort of real world example to give you an intuition why is it happening this way or another. All these relationships that I will be announcing can be also proven mathematically, and you can even just try to generate an example data set and confirm to yourself that particular elements will be associated or not. But today I will be just giving you an intuition. So let us first consider the chain. This is our structure. And for illustration, we have the following example. Assume that we have a room and we have a light bulb in the room. Then there is a switch in the room that controls the light bulb. However, to make this situation a bit more interesting, we'll add some probability into this system. Assume that when the switch is on, the light bulb is on as well with probability, let's say 0.9. And it is off with probability 0.1. So the situation that we are modeling follows the real world example, however, with some probabilities to make it a bit more interesting. Then, naturally, when it is off, the light bulb is off with the probability 0.9 and it is on with probability 0.1. Then there is also a switch in the house that controls all the electricity. And again, the same situation. If the switch is on with the same high probability, for example, 0.9, the electrical current can flow. And if it is off, again, with the high probability, we stop the current, and with the low probability, it can still flow. So now the question is the following. If I know the state of the light bulb, does it tell me anything about the state of this switch that controls the electricity in the house? And the answer is yes, that if I observe that the light bulb is giving me light, it's on, then with very high probability, this switch is also on. And inverse, if I observe that there is no light in the room, with high probability, the switch is off. And also association flows in another direction. If I switched on this switch, then with the high, and this one is also on, then with the high probability, we can observe the light in the room. So we will observe the statistical association flowing between these two nodes. Essentially what it means, we got our data set sampled from this situation. We have these three variables, x1, x2, x3. We said that there is association between the pairs x1, x2, and x2, x3. It means that just we take these two essentially arrays from the data set, like x1, x2, for example. And now if we calculate the correlation, this will be non-zero correlation that we'll observe. But as we already discussed as well, we will observe non-zero correlation between the two non-adjacent nodes, that is x1 and x3. Now, what will happen if we condition on the middle node? Conditioning I will be representing with this gray background of the node. Conditioning, this is an operation that we discussed last time, and what it means in reality is that I fix the value. Let me put it like this. I fix the value of the middle node. And in this case, this association flow will be blocked. And to understand it, let us consider a small example. Let us consider the case when this middle switch is off. Now, essentially, switching on and off this switch that is responsible for the whole house will not affect in any way the state of the light bulb. So the associational flow will be blocked. There will be no information flowing. What it means in the example with our data set, again, that if I condition, that is assume that my variable x2 has two possible values, it is either 0 and 1, and I split my data set depending on the possible values of x2, assume that here it is 0 and here it is 1. Now, if I consider only this part of the data set and I calculate association between x1 and x3, this association will be statistically negligible, close to 0. Are there any questions? Does it make sense, this example?
But the probability that x2 is still active if x1 is switched off is non-zero, right? Or it is assumed to be close to 0?
Yes, it is non-zero. But however, if I fix this value, I say it is now always off, because this switch implies the change in the light bulb. So assume it is off and this light bulb was on. Now, change in the position of this switch will not in any way affect the state of my light bulb, because I need to change this switch to have some change in the behavior of the light bulb. Okay, that's done.
Go ahead.
Yeah. Okay, great. So as I said, I'm just giving here an intuition. There are mathematical proofs available, but also the easiest way for you to prove yourself that this is true, you can just generate data set and use the library that we saw last time, and we'll continue with it today, to generate this situation, essentially to have one node that is the cause of another node, and then the third node connected in this such structure. Just sample from the data set and check statistical independence, and you will see that all this holds true. Great, now let us move to the second possible structure. Now we'll add the third node like this, and then we'll have the structure known as fork. And why fork? Because it's visually, it looks similar to this object, essentially. Again, the question is the following. Will we observe statistical association between x1 and x3 in our data set? And to illustrate this example, this situation, I will use the following example. Now, assume that we have two light bulbs in our room, and there is a switch in a room, and it controls the behavior of the light bulbs in the same way that when it is on, every of the light bulbs is on with high probability, let us say 0.9. When it is off, then there is no light, again with the high probability. Now the question, if I know the state of this light bulb, if I see that it is on, does it tell me anything about the state of another one? And in general, yes, because if it is on, we know that with a very high probability that the switch is on, and this fact of having the switch on implies with high probability that another light bulb is also on. So yes, there is statistical association flowing between these two variables. Let us again consider the same operation of conditioning. If we fix the value of the middle node, we fix the value of this middle node, Now let us assume that we have fixed the position that this switch is off. And I observe that this light bulb is on because there is a non-zero probability that it is on. Does it tell me anything about the state of this light bulb? And generally not, because I can assume that it is probably off due to the fact that the switch is off. However, the state of this light bulb doesn't tell me anything about the state of this one. So again, the conditioning operation breaks this associational flow between these two variables. And the final structure, when we'll be adding the third node in such way, and we'll have a structure known as inverted fork because of the visual connection to the previous structure. It is also has alternative names such as V structure because we have the shape of the V letter, or immorality. Immorality has some particular meaning. What essentially we have in the graph, we have two parents in the graph and a child, and the two parents are not directly connected. That's why it is called immorality. Again, we pose ourselves the same question. Will we be able to observe statistical association between the two non-adjacent nodes, that is x1 and x2? And the same thing, we'll observe an illustration. Now we have two switches in the room and one light bulb. And the situation is the following. If the two switches are on, then with the very high probability, let's say 0.8, the light bulb is also on. Then if one of the switches is off, let's assume that the light bulb is on with probability 0.5 to make it a bit more interesting. 0.05 and 0.05. And finally, then when both of them are off with very low probability, again, we can observe the light in the room. Now, the question is the following. If I know that this switch is on, does it tell me anything about the state of this switch? And usually not, because these two variables are not connected. So I can go and switch one switch on, but this process doesn't tell me absolutely anything about the state of another switch. So for this structure, as opposed to the previous two structures, there is no associational flow between these two variables, the two non-adjacent variables. Again, now if we sample the data set and we check the statistical dependence between these two variables, we'll observe that they are independent. What will happen now if we fix the particular value of the middle node? That is, we perform the operation of conditioning. Now let us assume that we observe the middle node, that is, we observe there is light in the room. Now, if I know that this switch is on, does it tell me anything about this position of another switch? And given our probability distribution, yes, now we know that this switch should be probably also on if we observe the light in the room. So here, unlike the previous situations, the operation of conditioning sort of opens the associational flow between these two non-adjacent nodes, x1 and x3. Any questions for this part?
So the probability is very low when only one switch is on, or it is 0.5 or 0.05?
Yes, but here we're talking about statistical association. So what I want to say that if we observe that the light bulb is on and we know that this switch is on, can we deduce the state of another switch? And because we know that with the highest probability, this switch should be also on in this situation. So we can make some conclusions. There will be statistical association between the two. Okay, if there are no questions, let us continue. Now we'll be using this theory to reason about the connections between nodes in an arbitrary graph. Let us assume that we have a graph like this, and let us discuss, we can have multiple paths between the nodes. For example, we have x1 and x2, and there is one path that is directed path. We are following the direction of the edges, and there is an alternative path that is undirected path, because sometimes we are following the direction of the edges and in other times are not. Now we'll be discussing when the path is blocked. And the path blocked means that associational information doesn't flow through this path. And as we discussed here, we'll be using these building blocks. What we need to block a path. So a path is blocked if there is a chain or fork with conditioning on this path. So essentially, if we observe this situation or this situation, and we apply the operation of conditioning, then we know that the information cannot flow from x1 to x3. And of course, if there are more nodes, for example, because we have block here, it will not be able to flow further. So if there is a chain or fork with conditioning on the path, or if there is a collider is the name of this middle node in the inverted fork, without conditioning, and also important, none of its descendants also has conditioning. So we were not discussing it, but essentially the idea is the following. If I have such structure, we said that conditioning on this middle node opens up the path between x1 and x3, and the same effect we'll observe if we condition on the child of the collider. It will again open up this path. This I will not be discussing, but if you are interested, you can check in the literature later. Let us now consider this situation on the graph, and let us think if the paths are blocked or not. We'll first talk about the first path, that is directed path. And here we have the chain and again a chain. And we see that this middle node is observed, it is conditioned on. It means that this path is blocked. Now, the second path, this is undirected path. And what do we have here? We have here a V structure, a collider, and it is conditioned. It means that this path is open now. Then we have a chain and no conditioning. So it means that association is flowing through this path. These notions of blocked and unblocked path is closely related to the notion of disseparation between nodes. Disseparation stands for dependency separation. And essentially, when all the paths between two variables x and y are blocked, it implies that these two variables are disseparated, they are independent. So the disseparation in the graph implies the independence in the probability distribution. Now the question, why do we need all this theory? And the answer is very straightforward, because when we are talking about the graphs, the causal relationship is following the directed paths. And when we are following non-directed paths, this is the spurious association. And we said that we want to somehow separate the two. And our tool to do that will be to block non-directed paths. And in this way, when we will be blocking, we'll be essentially able to measure only causal association. And this is essentially what we did last time as well, when we were considering the backdoor adjustment. So we have our treatment, our outcome, and we have the common confounder. And we said that we want to block this path essentially because it is non-directed path. And what we were using the operation of conditioning to do that. However, now this process can be generalized to arbitrary graphs. They can be bigger, they can have more difficult structure, and not only have this structure, that is this structure like here, but other types of connections as well. So for example, in this graph, we have directed path like this. So we don't want to block it, but we also have the two undirected paths that we want to block. Now we can reason. The first path, it has we have the fork here, and we have the chain. And we know to block it, we need to add some conditioning. So we can either condition on this variable, or on this variable, or on both. And like this, we'll be able to block the path. The second path, we have here a V structure, And we know that without conditioning, this path is blocked. So we can, this path is already blocked. We only need now to block this one, and then the association that we measure will be explained only by causal association following through the directed path. So this process is already automated, and you can even find libraries that do this, and I will show a small demonstration today. Now the question comes, what if I have unobserved confounder like this? So I know that there is a path exists, and for example here it is a fork, and I know to block it I need to do conditioning, but this variable is not present in my data set. Is there any other way we can solve this situation? And today I will show you one of the possible solutions. First, I would like to introduce you to so-called do calculus. Do calculus was proposed by a researcher. His name is Judea Pearl, and he introduced this do calculus. It has 3 rules, and what it allows us to do is essentially for an arbitrary graph, if it is possible to identify the causal structure, essentially it is possible to block somehow the paths, keeping only the directed path open, then this system of do calculus allows us to identify it. As I said, this process is already more or less automated. Pearl introduced notations known as do operators, and they are essentially have the same meaning as potential outcomes that we discussed last time. So potential outcome, what would have happened if the value of treatment was set to a particular value. Do operator essentially the same, which value the variable y takes if I set the variable t to a particular value. That is, I do t equals 1. So this is an alternative notation that you can encounter in the literature. And essentially what we want to do, if we have in causal queries, we have some potential outcomes or some quantities with the do operators, and our goal will be to express them using only statistical quantities. And this is what do calculus allows us to do if this quantity is identifiable for a particular graph. As I announced, there are ways to overcome the unobserved confounder problem, and I will show you one of them that is known instrumental variables analysis. And it can be used when we have a particular structure in our graph. And we will also discuss it with the demonstration a little bit later. So the instrumental variables, to be able to use it, we need to have a particular structure. And this is a canonical representation. We have the treatment, we have the outcome, there is a directed path, but there is unobserved confounder, so we cannot use the backdoor adjustment. However, there is another instrument, there is another variable z, that is, we'll be calling instrument, and it is a valid instrument if it satisfies some conditions. In particular, the first condition is relevance. Z is the cause of t. The second, exclusion. Z and Y are connected only through t. So all the causal relationship between Z and Y goes via variable t. And the last one, unconfoundedness. So there are no unblockable backdoor paths from Z to Y. And as we see on this structure, there are no backdoor paths at all. So this condition is satisfied. Now, if this condition is satisfied, and we have, I will now show you the case of linear relationship because it is the easiest one and we can have proofs for it. If the relationship is not linear, we need to consider every case and see if the structure is identifiable or not. But for the linear relationship, it is very easy to do it. So we now assume that all the causal relationships are linear. That is, t is the linear function of z plus some noise, and y is the linear function of t plus some noise. And also the way u is incorporated is also linear. So y will be essentially t is the linear function of z and u plus, let's say, alpha u. And y also has a linear component of, let's say, beta u of the confounder u. Now, the slight step away, how do we measure the causal relationship between the variables when we have the linear case. We will come back to our definition of causal relationship. We say that the causality is how much the outcome changes when we change the value of the treatment by, let's say, 1 unit. And for linear case, in general, this is the definition of derivative. Yeah, how much the value of the function changes if we change the value of another variable by 1 unit. And in the case of linear relationship, the derivative is just the coefficient. So this will allow us to identify, to know what is the true causal relationship between our variables y and t, and to see if our estimation will allow us to estimate this value correctly. Now, which method we'll be using? We'll be using the method known as two-stage least squares. And the idea of the method is the following. First, we'll take our data set and we'll regress the variable t on the variable z. So we construct a linear model that predicts us t as a function of the variable z. Then we'll use this model to predict the new values t from the observed value z. So I will show a demonstration. Maybe it will become clearer now. And then we will use this predicted value to estimate the causal effect on y. And why? Because essentially when we are doing this prediction of the new values t star, when we will be calculating the values of t, we'll be using only the variable z. That is, there will be no connection between the variable u and the variable t star. For calculating t star, we used only z. And this will allow us to estimate the true causal relationship. By the way, the operation of conditioning that we saw last time in the case of continuous variables is equivalent to just including the variable into the predictive model. So now we'll be including the variable into the regression model, and this will be the same as the operation of conditioning. To understand how we consider the demonstration now. So you should be able to see my screen. Here we'll be using the same library that we saw last time to simulate some structure. And the structure is essentially the same as what is presented on the slide. We have the treatment, we have our outcome, we have our confounder U, and we have our instrument Z. And we will be considering some cases when we assume that this variable is not available on the data set. So we cannot use it to do the backdoor adjustment. Let us have a look on the functional definition. We have z is a random uniform, u is some also random variable, then t is a linear function of z and u. And y is the linear function of t and u. And from here, as I said, we can already estimate what is the true causal effect. It is the coefficient for linear models, so our correct value should be equal to 3. Now we can generate sample from this data set. Here I show some visualizations to confirm that the data set is the way we expected it to be. For example, we can confirm that the type of the distribution for the variable u is normal. Do some other checks. And we will try to estimate now the causal relationship. First, we'll try the naive estimation as we did last time. So last time what we did, we had a discrete model, and to calculate the causal relationship of t on u or w, what we were just doing was splitting our data set depending on the value of t and calculating the mean value of our outcome in every case and then subtracting them. So this was the operation. Now, as I said, for continuous variables, this will be equivalent to including the variable into the predictive model. So what I will be doing here, I'm building a linear regression, and I'm regressing the variable y on the variable t. I'm including t into the regression set for calculating the variable y. And then I will just take the regression coefficient as my estimation of the true causal effect. And we can get here the value that is almost 4. We can again calculate the error of our estimation, and it is almost 28%. So like before, when we have common confounder, this naive estimation doesn't allow us to estimate the true causal effect. Let us try to do the correct estimation. Now we'll be trying to use backdoor adjustment as before, because this variable is essentially present in the data set. So I just want to demonstrate how the backdoor adjustment works in case of linear models. So what we'll be doing here, as I said, this process of checking the estimation, identification of the model, that is do calculus, is automated. And for example, here there is a function of this library where we can check, we essentially can ask what is the correct backdoor adjustment for this particular model if we want to identify causal effect of t on y. And it gives us, we can condition on u. This is the correct backdoor adjustment. And we can check, for example, if it is the case. So now we'll be simulating backdoor adjustment. We'll be regressing y on two variables, t and u. And again, we'll take the regression coefficient as our approximation of the true causal effect. And here they are plotted. This is our regression coefficient that we obtained. We can calculate what is the deviation from the two variable, and it's like negligible, very equal to, very close to 0. So using backdoor adjustment as before allows us to correctly estimate the true causal effect. Now the question, what if we didn't have had this variable u in our data set? Is there any other possible way? And as we discussed, we can try to use two-stage least squares method. Here it is. Essentially, what we'll be doing, first we regress the variable t on the variable z. And then we calculate the new values, these were t star, by predicting, using this regression coefficient, predicting the values of t from the given values of z. Then we do another next stage regression. Now we regress y on the newly calculated values of t, this new t, and we take the regression coefficient as our estimation of the true causal effect. And again, we can compare it with the true value that we know it is 3. And we see that now we are very close. From the error of approximately 28%, we reduced it to below 1%. So this method indeed works. Here I just put all of the estimations together to have them like in a compact place and be able to calculate, to compare them. This is our backdoor adjustment that gives us 0% error. This is our direct naive estimation with almost 30% of the error, and two-stage least squares method that gives us quite a good estimation with the error less than 1%. Now, this method is sensitive to the strength of the instrument, in particular, how strong is the causal relationship between Z and T as compared to U and T. So we will consider now this model where this is the functional definition of T, and we see that U, the common confounder, has much more effect on the treatment than the Z. And here we have the fear essentially that our prediction of new values of t to star from z will be not good enough to cover all possible values of t, because this variable has very low effect on t as compared to another one. Let us see what happens. Again, we have our naive estimation, backdoor adjustment, and the two-stage least squares. Here, what we can observe, essentially these two cases did not change, but the naive estimation is now giving us 10 times less error. And still two-stage least squares gives the better estimation. Now, what will happen if we increase it even further, this impact? Now you can observe that the coefficient in front of u is 2000. Similar situation happened. These two methods work, and now the naive estimation gives us the value that is very close, like essentially it gives us the same error of estimation as the two-stage least squares. However, the fundamental difference between these two cases is that by increasing the sample size, we can improve the estimation of statistically correct quantity, that is two-stage least squares, but our naive estimation will be not improved. And this is what is shown here. When I add more data, this estimation is improved and the previous one is not. And the last case that I will present here is that when common confounder has much stronger effect on both the treatment and on the outcome. And here again, we can see that naive estimation doesn't work. Backdoor adjustment works perfectly. Our two-stage least squares now doesn't work good. So the instrument is weak. But again, the same solution, by increasing the sample size, we obtain the situation that the two-stage least square starts behaving better, but nothing changes with the wrong naive estimation. Are there any questions?
Are there the questions for the end of the presentation, or you will continue?
If I have just a little bit more of information, so if there are no questions for this part, I will continue and then we'll finish today's talk and we can conclude with the final questions. Okay, no questions for now, so I showed you one of the approaches, the instrumental variables, that can be used when we have unobserved confounder. However, this is not the only possible case. There are other approaches as well that exist, and some of them are in fact very intuitive and very easy even to come up with. So I will just give you an intuition and I will give you some references. If you want, you can have a look a bit later, dive into this theory. The first of them is matching. So we have the problem when we have the common confounder and is not observed. That means that our treatment is not assigned in the equally proportional way to the different potential outcome groups. One of the possible solutions will try to match by the values of the confounders. So we'll try to have our treatment and control group more comparable. For example, here we have two variables, sex and age. And in the treatment group, I have one element that male and the age 56 and another female, age 47. And then I have another group that is much larger and has much more diversity. So now comparing them two directly is not fair. But what we can try to do, we can find the best matches for every entry of my treatment group. And treated group is where I have the value of treatment equals 1, and here I have the value of treatment equals 0, and then compare these two subgroups. So for example, we need a male. These are possible males. And we choose the one that has the closest value of the age, that is this one. So these two elements will be selected. Female, age 47. These are my females. So probably the closest one will be this one. So as I said, I will not be considering this whole group, but only the chosen, the matched entities, and I will use them to calculate the true causal effect. This can also be a possible solution. There are different variants of how we can calculate the matching. This you can check later if you are interested. Difference in difference will be a bit more difficult to explain. So I will just invite you, if you are interested, check this link, very nicely explained with the example. And I will use this time to introduce another thing that is known as regression discontinuity design. Here again we are interested in measuring some causal effect on one variable x on another variable y. Let us, and to better understand the situation, I will give you an example of a situation that we might be interested in. Assume that we want to measure the effect of having a diploma of recognition on our possibility to enter or be able to study at the university. This research was done in US. So this diploma is given, our variable is grade, and it is given only when your grade, for example, is above 10, if we have the scale from 0 to 20. Now, naive estimation would be to take all the people who have the diploma and all the people who don't have the diploma and compare them. What will they be? Will they be able to study at the university later or not? However, this comparison is not fair because people in this group, they have higher grades, so they are probably more intelligent. That is why they have more chances to enter the university than the people in this grade. So how can we overcome this problem? And the solution is the regression discontinuity design. And what we'll be doing here, we'll be comparing not all people, but only people close to the edge. And why? Because we say, let us take this margin. Here we have people that have grade 11 and grade 9. The difference between these two groups is very small. It might be just that the person didn't sleep well enough last night. That is why he was not able to get one more point to score 10 and get the diploma. So the difference between these two groups is not due to the confounders, but solely due to the random factors. And then we can compare these two groups, essentially measure this discrepancy between the two groups at this cutting edge. And we can say that the association that we'll be measuring is due only to the causal association and not the spurious confounding association. Again, just check this link to learn more. And also modeling, I will also skip. Just check this link if you are interested. These are some ideas of how we can overcome this problem of common confounder. And there are solutions that we can use in practice. We essentially don't need to reinvent them. And then I will stop here today's presentation, and I will be happy to answer your questions if there are any.
Thank you, Marharyta. So let me open the question part of the lecture today. Just a general question. Is it possible you to gather all the literature and send it to me, and I will upload it to the website?
So in the presentation, I have a link that apart from the links, for example, here for all these methods, you have the links. You have the links here. And also I prepared this document that contains some ideas for further reading, some books, and also some references to the researchers who are currently actively working, in particular in causal machine learning. So you can check those and yeah, get to know more what is current state of the art, what the people are doing.
Okay. Correct. So maybe I will just take it from this document. And,
yeah, just take it from this document. Yeah.
Okay, great.
Any other questions?
You partially answered this question in your presentation, but can you elaborate a bit more? What if the dependence is not linear? You shown already this example with the step change between the variables, but does it create severe problems in reasoning?
So if we have, like, for example, I presented instrumental variables. When the relationship is linear, we have the theory that proves that it works. And essentially, to prove it, I need the assumption that the relationship is linear. I didn't show you the proof, I just showed you that it works. It is also possible to prove it for some other cases. So now, essentially, what we are doing, we are imposing more assumptions on our model. Now we'll be imposing functional assumption on the functional form, that this should be linear model, this should be like quadratic or whatever type. And for different situations, there are some proofs that already exist. It depends also on what is your current problem. You can try to check if this method can be applicable to your problem or not, just following the same idea of proof. Instrumental variable is not the only one. As I said, another possible idea, regression discontinuity, but here we in fact again assume linear relationship. Or we can do regression, nonlinear regression. We'll talk a little bit more about it in the next lecture. A possible very naive easy way, for example, matching. Here, so we don't have linear relationship, but we'll be by matching. Essentially what we are trying, we want to reduce the effect of this common confounder. So we'll be removing this link, and then the association that we have in the data set can be only explained due to causal association. So this is also one of the possible solutions. So there are many. It depends on what is your problem that you are working with. Why there are so many results for linear relationships is because, again, we are coming back to the historical view of the problem. As I said, it was first introduced, and a lot of work has been done by people from social sciences, like economists and so on. And in their practical applications, often the relationships are linear. And even if you think a little bit more into this direction, if we consider some practical situations, not like we're not modeling physical processes, but we are modeling some relationships between in the situation involves human and some social processes. Linear relationship, what does it say to us? That a unit increase in the value of the treatment results in the same change in the value of the outcome. So essentially, linear relationship tells me that the change in the outcome is the same regardless of the fact if the treatment changes from 0 to 1 or it changes from 2 to 3. And in practical applications, when we are working, especially with the systems involving humans, so the problems are not complicated physical problems, oftentimes we can default to linear relationships.
Yes, but the example with the switches is not this case, right? If there is this heaviside dependence.
With example with the switches, it is binary case. Yes, I said it is either on or off. So it is even easier. This is something that we saw last time. Any other questions?
So the video, the presentation, the lecture is recorded. So is there any question? The lecture is recorded, so everybody can listen to this for the second time, and maybe he or she will come up with some questions and can contact Marharyta directly.
Yes.
So if there is no more question, thank you, Marharyta, for your very nice lecture, for all the explanation. We'll have a third lecture in 2 weeks. So feel invited to this lecture, and also feel invited for the presentation next week of Fabio Guzzolini. Have a good day and see you next week.
Thank you. Bye-bye.